Did it start? I don't see myself. Oh. So I don't see anyone. Hello? I don't see anyone. So is it? Am I supposed to see myself there?
Yes, sir.
Yes. But the camera is somewhere else. Is it this camera? No, it's not this camera. And also there is some delay, it seems. What I see here and when I talk to you. या तो आप वहाँ फोकस कर दीजिए या तो
सर वो फिक्स है।
कोई बोर्ड पे लिख करके भी बता सकते हैं वहाँ पे, यहाँ तो बताना मुश्किल है।
वो आ नहीं रहा था इसलिए मैंने सेलेक्ट किया। नहीं वॉल्यूमिनस तो चल ही रहा है फिलहाल। कर दें, कर दिया।
No, it's not. It seems it's LED.
सर ये
there is huge potential, and I think in India, if you see, most of the groups now have started working on sensors and biosensors because there is huge potential and huge market. I showed this slide, I think in the lecture one, where you can see that the biosensor market growth is about $2 billion per annum. That was predicted. Now, after the COVID-19, you can see that how important it is to have biosensors for detection of COVID-19, which is fast and cost effective. So these are the challenges. So there is huge market, okay, and optical sensors are catching up. So it will be very interesting to see. Apart from this, I think we will be doing. If you have some questions, of course I will be happy to answer. Regarding the question paper format, practice question paper, I would say that you should know what are the components of a sensor and what are their characteristics. That's one part. That after doing this course, we want someone to learn about this. Okay, so it is very interesting. You should know this. So what are the components? There is source, transducer, sensor surface, source, transducer, detector. So these are the certain things, and what are their functions. Coming to the characteristic parts, there are two important characteristics. One is sensitivity, and the other one is detection accuracy. Another one is limit of detection. So I had told in my lecture very clearly what is the difference between the limit of detection and the sensitivity. How you calculate sensitivity? You differentiate the response curve. Response curve means if you are measuring change in intensity with change in concentration, then if you plot this curve with concentration on x-axis and intensity on y-axis, the slope of this curve, that will define the sensitivity of the sensor. So if I give you a question and I ask which sensor is having better sensitivity, what you will do is that simply differentiate this response curve. When do we call a sensor to have linear response? A sensor has linear response when the sensitivity is constant. Sensitivity is constant. What is changing? The response curve is changing. Okay, so it seems that my volume is a bit low. Now is it better? I came a bit closer. Is it better now? Palina, is it better? You can write. Okay, there are other things. Apart from the sensitivity and this thing, then you have optical part. What is in the optical part? I told you in the very first lecture what are the things which are important in detection, in optical based detection, and there I told you that if you have a plane propagating wave, what will be its direction, what will be its polarization, and then I told you about the polarization dependent sensors. We discussed in detail the Brewster angle based sensors and Evanescent wave based sensors, and these are two very important aspects which are of interest. Okay, so you should know what will happen if I change the angle to this value, what will be the penetration depth, what is the minimum value of penetration depth, what will be the maximum value of penetration depth, what are plasmons, plasmons, so you should be able to understand. You should try. You should see yourself also that what will happen if I change the metal dielectric function to 2 times or 3 times. What will be the effect? Detecting visible light using spectroscopy. There are, I think, a lots of papers. So reference for detecting visible light using spectroscopy. I mean, this question is not correct, but let us say if I understand, you want to see, you want to know about optical spectroscopy based sensors, right? Optical spectroscopy based sensors, there are huge, I mean, few of them are we already discussed in the lectures. You can see from lectures 9 to 12, not 9 to 12, but 9 to 15 or 16. This whole part covers detecting using optical spectroscopies, and there we discussed what are enhanced optical spectroscopy like surface enhanced Raman spectroscopy, surface enhanced fluorescence. So these are all references. I mean, there is huge number of references. You just type it on Google and you will get thousands of references for everything. Now detecting visible light using spectroscopy, that is, I think, when you are going to detect, that is the detector part. This is not a sensor part. Detector is a part of the sensor. Okay, so be careful here. Okay. Whenever we are going to make a sensor, actually detector is an integral part of the sensor. So when light of, let us say, visible light, white light is coming, and we have the detector, it actually has a spectrometer, and the spectrometer resolves all the wavelengths, and then it detects the power corresponding to each wavelength. Okay. So these optical spectrometers, be it a Raman spectrometer, UV visible spectrometer, fluorescence spectrometer, these are all detection of visible light using spectroscopy. Okay, now Palina asks, what is plasmon waves? You see, it's very interesting. If you remember, I told you that when light goes from a high index medium to low index medium, and if you are incident at an angle greater than the critical angle, then there is total internal reflection. Okay, and in total internal reflection, if you see the electric field profile of the evanescent wave, that is something very important. Try to understand this very carefully. It has two components, one in the x direction, one in the z direction. In the x direction, the electric field, the k wave vector component is real. Wave vector component is real. If you write the electric field vector of the evanescent wave, you will see that it is real. And in the z direction, it is imaginary. Okay? Z direction, it is imaginary. So that's why the wave was not traveling in the z direction but only in the x direction. So evanescent wave is a wave which travels up to infinite distance and its field decays. It doesn't die out, it goes on. Now if you take the other medium as metal, so this wave vector which was in this direction, this x direction, z direction, it was imaginary. Now x direction, if you take n is equal to n plus ik, then it becomes a metal, and in metal then again there will be an imaginary term. Okay, so that imaginary term will lead to decay of surface plasmon wave. So surface plasmon wave is a wave which travels along the interface and its field is decaying both the media, the metal and the dielectric media, while it travels. And since its wave vector is complex, is imaginary in the z direction, in the perpendicular direction it is imaginary along the interface. It is complex. In perpendicular to the interface, it is imaginary. The wave vector is imaginary. along the interface, it is complex. So if it is complex, that means the wave will travel and it will die out also. So that's why in case of evanescent waves, we define only penetration depth. But in case of surface plasmon waves, we define penetration depth as well as propagation length, because after certain length it will die out. So this is something which is very interesting. Okay, so I hope that you understood what is a plasmon wave. Plasmon wave is a wave, and it's a it's a plane wave actually. If you can resolve these two components. So electric field will be dying in the z direction and also along the x direction, while it is traveling along the s direction. So this wave is traveling at the interface. Its field is decaying in both the media. Okay, and like you can understand it like this. Suppose you are traveling on a bike, and let us assume that bike separates two sides of the road. Okay, and you are stretching your arms. So when you are traveling actually and you have stretched your arms, so this kind of wave is the plasmon wave. Plasmon wave is, and also you can assume that the bike is decelerating. The bike is slowly going to speed 0. So it is like this. So you have extended your arms. These are the penetration depths in both the media, and also it is going to decay. Okay. I don't understand what Abhi Raut has asked. Sir, आज एग्जाम आहे प्रिपरेशन नहीं झाले, only MCQ वाचून जमेल का? I don't understand this. I hope if you could write in English, or then it will be better. And don't understand this language. One more thing which is important about plasmons. Yeah, you know, center and surface plasmons, there will be good number of questions, so be prepared. Brewster angle based questions, critical angle, SPR, plasmons, Raman enhancement. You see how the Raman power goes with distance, and how the Raman electric field will enhance. There are two different things. So I think there is a slight mistake in the slides also. You should go and check. Electric field amplitude is the square root of the intensity. So if I say Raman power or Raman intensity, that means it is the squared value of the electric field. And if you want to see electric field enhancement, then it will be the square root of the electromagnetic field, electromagnetic power. It's not the same. Okay, they are different things. There, the electron, the exam is MCQ type only, and exam is MCQ, and also it has, actually there are three types of questions. One is like you give a sentence and it is like true and false, you have to predict, or out of 4 options you have to find out one option. And there are certain questions, few questions only, where you have to fill in the blanks. Okay, I hope you understand what is transverse electric wave, what is transverse magnetic wave. There is something which I try to explain very clearly, and I warn the students that they make this kind of mistake whenever it is required, whenever it is asked. This course, this exam will have questions from all the sections. So don't miss the circular dichroism, or terahertz spectroscopy, or biomedical optics, when I discussed the questions on the section on tissue optics and all these things. So you have to be very careful. The exam will cover all the topics. Okay, where you had these molecules, and most of the things will be optics only. Like when we start, traveling from one medium to other medium, then you have total internal reflection. Also, when you have total internal reflection, or even send wave sensor or surface plasmon wave sensors, we use a prism. Okay, we use a prism. So the angle which is the angle of incidence is different than the angle at the interface. So you have to be careful. This angle is different. Suppose you have a prism of material 1.5 refractive index, and you are incident at an angle theta 1 here. Then in the prism it will get refracted, right? And then if you have multiple coatings on the other side of the prism, this theta, let us say theta prime will be different than theta 1. So there is a distinct relation between this. I think you should go and derive this also. Okay, so this will help you in understanding. If I ask you the sensitivity, for example, on certain value of the concentration range, what is sensitivity? You take the slope. How are you going to take the slope? y2 minus y1 divided by x2 minus x1. This gives you the slope, right? At that particular value of the concentration. Anything else you want to ask? Yeah, so we will be discussing. We already talked about plasmons and the wave vectors and propagation constants. What happens? Let us say if you double the refractive index of metal, if you, let us say your refractive index is increasing from 1.33 to 1.35, how will the penetration index change? How will the refractive index change? How will the propagation length will change? So these are all the things you should know. Okay, what will be the minimum value, what can be the maximum value, what are the angles at which you can get minimum or maximum. These are few things which you should be able to understand and quantify. Okay. Okay. So electric field vector perpendicular to the plane of incidence. I am happy that at least one student is very actively asking questions. I wish that others also can ask. Okay. So transverse electric means electric field is transverse to the plane of incidence, 90 degree to the, or you can say perpendicular, which you have written correctly, transverse electric. So transverse magnetic means the magnetic field vector will be perpendicular to the plane of incidence, but we are only concerned about the electric field profile. So when magnetic field is perpendicular to the plane of incidence, that means in transverse magnetic, the electric field vectors will be in the plane of incidence. Electric field vectors will be in the plane of incidence. Okay. And problem solving, I told you how to do, and you should be able to see. First of all, you must be able to be familiar about the electromagnetic wave, how it propagates, what are the directions of propagation, and how you define the polarization. All these things are important. Once you know this, then you can say what kind of sensors are there. Now you take this plane electromagnetic wave, it is incident on an interface. You can see what are TE polarizations, what are TM polarizations, and how the reflectivities and transmissions vary with angle. For TE and TM, at certain angle you get Brewster angle, you get polarization by reflection, and from there you can conclude certain things. You can make sensors, you can calculate sensitivity. Then we do it other way, and also there is a Brewster angle, and then total internal reflection. We get evanescent waves. We should know the properties of evanescent waves, how it can be used for sensing. Once we know that, then we make the other medium also complex, and then we have surface plasmon waves. And in surface plasmon waves, there are lots of things which I told you that you should be prepared with. And then once you know this, there are certain excitation there are certain issues with the excitation of surface plasmons. Then you go to localized surface plasmons. Localized surface plasmons will tell you the electromagnetic field enhancements and how we can use them for sensing, that also I told you in the class. And once you know that, and you know the electric field enhancement near the surface plasma structure or localized plasma structure, you can use this for enhancement of spectroscopic signals or optical signals. So for example, we discussed surface enhanced fluorescence, we discussed surface enhanced Raman, and there I told you that what are the factors on which these enhancements depend. And I told you that in Raman, what are certain limitations and how can we overcome these. For example, I told you the distance dependence, and then I told you that we can overcome it by certain technique, and then I showed you certain sensors, also the real examples which are from the literature which are already published, and then we move to the optics of materials like tissues and cells, and from there we could and biological cells, and from there we could see that many a times it is possible that we don't attach a receptor layer, and it directly can work as a fluorescent or optical sensor. And I showed you the examples of bilirubin detection, hemoglobin detection, and there are certain examples, and certain proteins also, they already have fluorescence. So this is something which is which can directly be used for sensing. You don't need to make a biosensing surface directly, because light, when it interacts with the molecule directly, it will give certain modulations to the input light, and that once detected will give you change in the signal. So that directly makes a sensor. Suggest some student projects on sensors at PG level. Yes, it depends. Sensor projects, there are huge number of sensor projects. For example, this evanescent wave sensors, at PG level, I think students can learn how these sensors work, and then evanescent. I told you about the evanescent wave engineering, the penetration depth, how we are improving the penetration depth up and down. And if you take the medium which is absorptive in nature, then you can if it is absorptive in nature, what you will do is that it will absorb certain wavelengths, and then you can make a sensor out of it. So at PG level, you can work on a project of TIR based sensor or even set based sensor. S polarization in TE is nomenclature. You call it S polarization or TE polarization, and similarly TM polarization you also call it P polarization. Okay, that's the nomenclature only. Yeah, I was talking about the projects, student project on sensors at PG level. So evanescent wave sensors is one project. You can use it for detection of, let us say, amount of sugar in orange juice. Like lots of companies are selling orange juices, and some of you mean S? Yeah, S is I think I didn't go into the nomenclature, but I would say S should be surface, which I believe that when P polarization means I think we can ask Google about it. I'm not sure about the nomenclature, but how I understand it is like P polarization means it is perpendicular to the interface. It is perpendicular to the interface P, and S is like on the surface of the interface. So it is either on this surface or this surface. That's T polarization, and P polarization is like perpendicular. What I'm saying. Okay, this is what I think. Yeah, there are huge number of PG projects. There are few students who are already working. I told you the designing of the nanostructures for plasmonic, guided mode resonance based sensors, block surface wave based sensors, multi-layer films. I told in this class that how we are going to simulate, how we are going to theoretically model a sensor, optical sensors, made of multiple layers of, and you could use couple of layers as metals and permutations and combinations of dielectrics and metals, and then you can simulate. So there are, for last 1 year, because of this COVID, we are only doing projects online only, and in online mode of teaching, we are generally using simulations only, doing simulations only. So in the simulations, it is mostly writing codes on MATLAB, or there is a free software also, Octave, which you don't need to purchase. It's similar to MATLAB. You have Python, which is like open source code, and people, you are using it for simulating or theoretically modeling sensor surfaces, sensor structures. You can make grating like structures. You can make double gratings, two-dimensional gratings, or if you make it like three-dimensional structure, it will be like a photonic crystal. So there are certain applications based on this. Okay, if you, you keep on adding the complexity and you make a difficult project, and then you can fabricate and make sensors out of these simulated ones. First you optimize the structure, optimize the performance of this structure, and then you use it for sensing applications. Okay, there are a few things which students can do at UG and PG level. Regarding the exam, I told you that it will be 50. I told you that it will be MCQ and fill in the blanks. Few questions, and few questions will be like true and false, and it encompasses 3 sections also. Like few questions will be from the slides. If you did the assignments well, you should go and revisit the assignments also, and not only that, you should go and see the lectures also. So there will be like lectures. Then from the lectures there will be questions, which will be like bit of thought provoking, where after seeing the lectures slides, you will be able to understand, and if you attended my lectures, then you will be able to know what I mean. And assignments will also help you. Okay, assignments will also help you. So if you have any questions, you can write to me also, and if you don't have any questions, I think I have told you how to prepare for the exam, and also the important sections, and where you should be prepared with these questions, that penetration depth, propagation length, and the field profiles, how are these field profiles going, and the wave vector sign. It is important that you understand how the wave vectors are changing, and if they are real or imaginary, and or complex, and what are the consequences for the wave which is at the surface. Okay, and more important thing is that how we are using this simple optical phenomena for sensing. So if you are really interested in sensors, then you must know that what are the methods by which we can improve the sensitivity, selectivity, detection accuracy, and all these things of the sensor. Okay. For example, I told you about the sensors, let us say electrical kind of sensor, electrical transducers. So what will happen if you have interaction at the electrical transducer? It will either change current or change voltage, okay, or change resistance, inductance, conductance. All these things will change. But what kind of sensor it will be? What kind of sensors am I going to make? Which sensor will be? If I make a sensor, which of these should be measured? So that is something which is very interesting. So a sensor, for example, if you make a sensor chip, no, it can have multiple responses. For example, let us say that I make a polymer film. Polymer film, and I am going to measure moisture. Now, if I am measuring moisture using this polymer film, if you put it in the air and air is humid, what will happen? That let us say that it absorbs moisture, it can become thick. Its dimensions can change. Let us say that in one dimension, let us say that its thickness is increasing in this direction. So by measuring the change in the thickness, you can say that how much is the humidity, right? This is possible, and this will be a very simple sensor. Now, this sensor, its performance will also depend, which we call the response time, also depend how well, how fast this polymer cube is absorbing the metal, this moisture. How fast, what is the rate of absorption of water by this polymer, okay? Simple. Now, this is one characteristic. Second characteristic is that suppose there is this thickness of the polymer, and then you are shining light on it, and let us say I am using the transmission, and I see that the responses are fast. So there is another kind of measurement. Let us say that this polymer cube is also conductive. Okay, so when the moisture changes inside, there is a change in the conductance. So you can make another sensor. So out of these kind of three sensors, let us say I discussed the optical. So you can make from the same polymer cube, you can make a length-based sensor. You can vary the change in dimension. You can make an optical sensor. You can make a conductance-based sensor. Which sensor shall we make? What will it depend? There are few factors on which it will depend. The first factor is which one has better sensitivity. Sensitivity means the slope. How fast is the response? How fast is the change in that particular optical parameter? Let us say optical parameter is fast response, not response but faster change in the with the change in the moisture content. So the slope. So if I plot the sensitivities, so whichever sensor has better sensitivity, that means we should go for that sensor. Also depends on the cost of the sensor involved. Many times it does matter. Okay. For example, in COVID-19 detection, the whole world needed COVID sensors. And cost effective. We cannot put huge amount of money. If someone said like $10,000 rupees for one detection, will it be feasible for a country like India? So, cost is involved, response time is involved. You cannot make a sensor which is so slow. Many times it is required, but many times it is not. So you want to have a fast sensor also. So one has to keep in mind this parameter and the dynamical range. For example, Dynamical range is important, that we want from this range to this range. We want to sense from this range of moisture to this range of moisture content. So this is also important. So there are few guiding factors which will tell you in which domain you are going to work and which transduction method you are going to use. It's optical transduction method, conductance transduction, or length only. Okay. So this is something which I think people miss when they are going to make a sensor. Okay. Palina, do you have more questions? Okay. So these are certain important aspects, and there are certain, so depends on kind of application. When you are making a sensor, it depends on the kind of application we are looking for. For example, when it is very critical to measure the shape and size and the functional groups, all these things you use molecularly imprinted polymer based sensor. But if you are only concerned about the functional groups, you don't care about about the shape and size, and then you can simply attach the antibodies on the surface of the sensor. More important here is that the more number of components you are going to put, the larger will be, it will be high cost, higher will be the cost. So the cost is also important. Many a times the signal, let us say signal to noise ratio, is also important to understand. So suppose you are making a Raman based sensor, molar electricity, it is given there, it's just definition. Okay, see the definition, what it means. Electricity, how are you going to measure the electricity? First of all, you have to understand this. And if you understand this, then you will be able to understand what is molar electricity. I think you should go and see the lecture again. Okay? Definition is self-explanatory there only. Yeah. And who knows, you are asking a question which can be, Alright, in the exam also. Yeah, I was discussing about the putting the components. Yeah, so when, let me finish with this thing because it's something which is very important. When we are making sensors, I was telling that if you put more and more number of components, then it becomes more costly. What it means is that not only the cost is important, but also you see that many times the performance decreases. We are putting more and more components. Maybe you improve the detection accuracy, selectivity, and so on. But there is again something which is left, and that is signal to noise ratio. So many a times if you put more and more layers, many a times it is possible that you reduce, it leads to reduction in the signal to noise ratio, and that will affect the performance of the sensor. Okay, because detector has certain limitations, so you have to understand this thing. And these things you see, these are simple definitions. You can see the definitions. I think is here we discuss something which is which you cannot find. I think that these are simple definitions, and from definitions only you can find what is specific rotation, what is optical rotation, molar electricity. These are from evident from the definitions. What I'm discussing here is the critical issues which which one should understand when you are making a sensor. And I'm not yet finished with this. So, for example, if you are making a Raman-based sensor, and the Raman intensity depends on the distance of the not Raman, actually source based sensor, and the Raman intensity depends how close the molecule is kept near the surface. And if you put more and more layers, basically you are losing this signal from the molecule. If you are putting more and more link layers, let us say one cross linker, then another cross linker, then another something molecule, and then analyze, and then the receptor, and then the molecule, you are losing, you are making the signal sensor signal complex, and many times it won't be able to find that which interaction is leading to the sensing process. Okay, so it is very important that you understand these things. There is one more thing which I want to tell you. If you remember, when we discussed the components of a sensor, there I discussed that analyte is not a component of the sensor system, but analyte is the parameter which you are going to measure, or the molecule which you are going to sense. Now suppose you make a sensor surface, on top of it you put a receptor layer which is going to specifically detect this analyte, and then I told you that even if you put large number of receptors, there are still certain sites which can work as the centers which can give foul signal. So let us say that let me tell you that suppose you are having a chip and you are putting closely the molecules. Just a minute, I will show you in a minute this thing, and suppose it's closely packed. Let us assume that. So suppose you have this chip, and on the chip you have put this receptors which are, let us say, circular. Okay, so you can see in between the circles there is a gap. And what will it do? It can lead to non-specific binding. So non-specific binding will give you false signal. So what we did was we used something called anti-fouling agents. Anti-fouling agents we put on the chip so that it blocks all the sides except the receptor side where the molecule will go and bind, where the analyte will go and bind. So it is very important that we put the anti-fouling agents. But however good an anti-fouling agent you put on the sensor chip, it is not going to completely cut all the foul signals. No, it's not possible. It's not possible to have a sensor surface where molecule X goes and binds and molecule Y will go and not bind. It's not possible. There will be certain molecules which are very similar to this molecule. They can go and bind on the sensor surface. Okay? So one has to be very careful. So when you are making a sensor surface, it is always possible that you will have some foul signal. But how do we know if it is foul signal or not? How do we make our characterization curve in such a way that we don't that takes care of the fouling thing happening at the sensor surface? So what we do? So let us assume one example. Let me give you one example, and then I think with this example, we will be able to understand what I mean to say. Suppose I am making a sensor which is able to detect glycated hemoglobin. You know, glycated hemoglobin is a molecule which is most reliable test as of now for diabetes. So if a person has diabetes, you see that mostly people measure glucose concentration in blood serum. But this can fluctuate. Like if I go and eat 100 grams of sweet, and after 2 hours my sugar level will be high in the blood because it got it got into the blood, and then if you measure the glucose concentration or sugar level in the blood after 2 hours, let us say, after I ate the sweet, you will have high concentration of sugar in my blood. So this is not a, so this doesn't tell that if I am diabetic or not, because I ate something and then it reflects immediately there. When a person is diabetic, this hemoglobin on the hemoglobin, this glucose goes and binds on the hemoglobin, so it becomes glycosylated. HbA1c. So let us say that we want to detect Hb molecule, glycated hemoglobin in the blood, and from there we can conclude if the person is having diabetes or not. Okay, because if the person is having diabetes, it means that the glycosylated hemoglobin will be the concentration will be higher. Now I make a sensor chip and I put anti-fouling agents so that bilirubin can go, because in the blood you have bilirubin, you have certain ions, and you have glucose also. So blood constitutes lots of analytes and lots of molecules, hemoglobin also, and you never know that which one of them will go and bind on this sensor surface. And if it binds on the sensor surface, it will lead to change in the signal. So it is even if we put the anti-fouling agent, it is possible that this molecule, let us say bilirubin, goes and binds on the anti-fouling agent and gives a signal. So what will we do? We do correlation studies. When we make this sensor, while making the characterization curve, what we will do? We change the glycated hemoglobin concentration, HbA1c concentration, and we measure the output signal. This is the response curve. We see the effect of other parameters on the performance of this sensor. For example, if someone is taking more alkaline food, the pH will be changing. The pH of the blood, and it is possible that there is slight change. So what we do is that, what is the effect of pH? If someone is having high temperature, what is the effect of temperature? If someone is, and then the effect of these molecules, how these molecules are affecting the performance of the sensor with change in concentration. Okay, so it seems that there are a set of parameters which also govern the characterization curve. Suppose you are of my age, and we both are having the same value of glycosylated hemoglobin, but there are other parameters which in the blood which not necessarily are the same for you and me. So their effect will reflect on the characteristic of the sensor curve. What it means? It means that the characteristic curve which works for you Even if we have same level of glycosylated hemoglobin, it doesn't mean that that will work for me also all the time. Okay. It is possible that it matches. It's not possible that it will match all the time. So when it comes to biomedical sensors, biomedical detection, one has to be very careful because even if, for example, if we are detecting COVID-19 virus, we call it SARS-CoV-2 virus, okay? And when we want to detect this, if we make a false prediction that if someone is infected with COVID-19 and we say there is no COVID, it will be a trouble for others because it can spread. That the person will feel, okay, I don't have COVID, and then he goes into the market and everyone gets infected. So this is something which one has to consider while making a sensor. These are the practical things. Practical things. I mean, theoretically it's okay that there is a change in the signal, and when you have TIR, for example, TIR-based sensor. If you remember the analytical approach, where we discussed that when you have a particle interacting with the additional particle, interacting with the emission field, there was this perturbation theory, right? First order, we took we considered first order perturbation in the wave vector, and because of this, there was Cs, you have WBCs, you have platelets, you have other molecules, and their concentrations will affect the performance. So if you have dengue, your platelets count goes down. Okay, your platelet count goes down. But you are not. So see, there are sensors. There are sensors. There are methods. They are measuring the platelet counts, and from there they are predicting that you have a dengue or not. There are few things which people many times don't do. For example, detecting dengue, they are measuring the platelets. Why can't we detect the dengue virus? So now people are thinking this way also. So there are these kind of sensors also. So when it comes to the practical aspects, there are lots of things which you need to consider. Okay. So the sensor characteristic curve is something which is very important thing when we are making sensor characteristic curve, and we have to see what are the false negatives, how much are the false positives, and so on. And these things need, this thing can be done only we have performed lots of control experiments. We call it negative control experiments, positive control experiments, and from there we can conclude that the sensor is working for this range and this concentration, and the effect of nearest neighbor molecules for on the performance of the sensor. For example, if I am going to detect something in water, I must know what are the, let us say I want to detect how much is the sodium ion, but we should also know the effect of potassium ion on the performance of the sensor, which is measuring the concentration of the sodium ion in water. These are few things which are very important. Okay, so one has to understand what are the implications of this kind of sensor. Okay, so when you are going to do a project on sensors, when you are going to do research or project, or you are going to really make a sensor, it is very important that you calibrate and validate your sensor. And how you are going to do that? In calibration, I told you a lot. Calibration, I told you that when you are going to do calibration, you have to study the effect and correlation of the nearest neighbor molecules on the performance of this sensor, or the ambient conditions on the performance of this sensor. This is one part. Validation, let's assume that there are certain sensors in the market already. Let us say if you are going to make an optical sensor for blood glucose detection, we know already there are glucometers. If we are really adding certain value proposition to the product, it can go into the market. But important thing is that uh, you validate our device with an existing technique. Okay, so these are certain things which are important when you are going to make a sensor. So I think I will end this live session now. And if you still feel to discuss with me, and if you still have certain questions, you can write to me on my IITR email. Please note that you write to me on my IITR email, that is sachin.srivastava@ph.iitr.ac.in. Okay. So if n value of an light changes, how is the sensitivity affected? Please discuss question number 4 in assignment 2. Oh, I don't have this thing open at the moment, but can you please write me this thing in email, and then I will reply there. Okay. What kind of sensor it was? I need to see this. Okay, but the sensitivity, how is the sensitivity changing? Sensitivity is changing simply, you have to estimate the slope of this response curve. So if you are n is the value of the analyte, and suppose you are measuring change in some parameter, let us say voltage. So voltage versus n curve, and you are taking the slope, this will give you the sensitivity. So I hope I answered your question, but if you write to me, so that writing means that I will know your email ID, so I will reply you. I can go and see the question number 4 in assignment 2, but I can then reply you. Okay, if you drop me an email. Okay, so thank you.